say this again. If you remember, what we had before was this. That's energy. And we get an energy continuum, right? So all these values of energy were allowed. That's not the case anymore. Now, I have certain values of energy. So I only have this level, and then I have a gap, right? This is a gap. And then I have another level of energy, and then another gap, and I have this level of energy. So it's like a steps now. It's not a continuum. Remember that this C, it's equal to the constant, right? To this constant here. It's just the value of the constant. Okay? That's the value of C as you get there, okay? So what is this E1 thing? This is what we call the 0-point energy, right? The E1 that you see there, it's the first allowed level of energy, or the first energy value that will give a solution to the Schrödinger equation. What we see here, it's called an energy quantization. So basically, we're quantifying energy and we're dividing it into allowed values. And the lowest value of energy that an electron can assume or can get is that E1 energy, is that 0-point energy. And this is something I mentioned before. So the lowest value of energy that an electron can assume is not really at the bottom of the potential well. So if we remember the potential well, so this one is not really here. It's not really at the bottom, okay? It's slightly above that bottom. So it's somewhere actually here. It's just slightly above that bottom of the well. And that's the 0-point energy. That's the lowest value of energy that an electron can assume or can get. Is it clear, guys?
Yes, mister. Now I have a question.
Yep.
As these are the energy levels for electrons, are these the ones, I mean the levels, that when we were taught about structures like, you know, this electron goes in this orbit, this next electron goes in this orbit, and they always talk about energy levels. Are those energy levels the same as these ones?
Yes, it is related, and we'll get to that in a few slides. We'll see how this sort of satisfy the condition of the model of an electron, of the model of an atom, and why electrons move in this way, and you know why an atom. Because remember, at the very beginning, everyone thought atoms are all circular and electrons move all around the nucleus in a circular way, and you know they later said no, that's not possible. And so we'll see how this relates in a few slides to that model of an atom, and how electrons move around a nucleus, and obviously how that relates to the energy levels, and we'll actually make the connection of this to every type of atom in a material, so to metals, to semiconductors, to insulators. Yeah, we'll do that connection in a bit, but yes, it's basically related to that. Any other question, guys? No, okay, somebody's recording already. Okay, I forgot. Thanks, guys, for recording the session. Okay. This is just a side note, okay? Because this will become more important soon. So I just want to mention this now, so everyone is clear. Everyone has their own on their minds, and just that, okay? This is just about probabilities, and I'm sure you have you should have seen this when you were taking either statistics or maybe even advanced mathematics. You should see this. And now we're gonna give it just a different meaning, right? We all know by now that this is the general form of a wave function, right? That's just a becomes just a constant, and that's just the general form of the wave function. We know that every function has its complex conjugate, right? That is just the opposite. That's the complex conjugate of the wave function. Okay, so far I think that's clear. Now, what happens when you multiply, or when you get the product of a function times the complex conjugate of the same function? Remember that basically becomes a probability, right? When you get the product of a function times the complex conjugate, did you guys know that? This is something they should teach you in probably statistics or yeah, usually in statistics, I believe, or something related, advanced mathematics, probability. Did you guys know that?
I don't think so. In statistics, we weren't thought about this, and many times they said we aren't going to show you the demonstration of this formula because it has to do with imaginary numbers. So just learn the formula and that's it. We never have like the insights of them. We don't know how it works.
Okay. Okay, we might do it in the tutorial then. Yeah, I'm not gonna also spend the time in this class, in the lecture to learn about how this probability works. But in short, for now, we can get a probability of a function, okay, and we'll give it the meaning now. But in general terms, we can get the probability of a function, or something related to the function actually, getting the product of that function times its complex conjugate. Okay. So if you get that the product, then in this case, because we're talking about an electron in a potential well, then this probability, that means this product, okay, it's gonna be the probability for finding an electron within the potential well. Why am I saying this? Because remember, guys, that I have this, right? I have the potential wells here, right? I have, this is the potential well, this is actually infinity, remember? Okay, those are the potential wells. I have electrons, or I can have electrons within the well, so that means here, right? I can have electrons here, but I can also have electrons here, right? So the probability to find an electron here, let me use another color. The probability to find an electron here within the well, it's the basically the probability of the function, that is the product of the function times its complex conjugate. So if you can multiply this and you will get 4a squared sine squared of alpha x. This might not be clear now in terms of, okay, why am I going to use this? But this will become very important soon. So I just wanted to mention, now that we're talking about electron in a potential well, I thought it's the best spot to mention this, and because this will become useful eventually. Okay, but this in general, it's the way to get the probability of something. Now you can ask me, why didn't we do this for the free electron case? Because we're talking about free electrons, there were no barriers, so basically all electrons were there, so it was 100% possible to get electrons because there was basically no barrier. I didn't have any sections. Here I have different sections. I have the well like inside the well, or I can have electrons outside the well. So here, right, I can have electrons outside the well. In the free electron case, I had nothing. I had just electrons all there, right? Is this clear, guys? Okay. So now, something important comes and appears. If we were to plot the wave function of the electron in a potential well, the 2ai sine alpha x, as I said, we can plot this, or sorry, this is always satisfied as long as n is an integer, right? And so if we plot this function for n equal to 1, we get this. And then for n equal 2, that's the next level of energy, remember? We get this, and for n equal 3, we get that. This is only in the A range. Can anyone see something? Just focus on this thing first, guys, on the first graph. What can you see there?
The period is becoming smaller.
Sorry?
The period is becoming smaller.
Okay, the period is becoming smaller, that's right. What else?
Natural modes of vibration.
Yes?
I don't know if that is related.
Well, I mean, it is a good observation, but what I want to point out here is remember that, or sorry, realize that for each level of energy, actually, so let's say for n equal 1, for n equal 2, for n equal 3, the waves you have, it's actually the same in that range, in the A range, it's actually the same as that value of n, right? So in the first level of energy, that means for n equal 1, you have only one wave in the A range. This is just A, right? I mean, you can obviously repeat this periodically, but in this range, in the A range, you only have one parabola or one wave, if you want to call it. I think that's actually a better term. And that in the same happens for n equal 2 and for n equal 3. We all see that, right? That would be the case. And before these concepts of quantum mechanics appear, people thought, okay, this is actually the probability of finding an electron. But then they said, actually, wait, that's wrong. We should do the complex conjugate. And that's what you have here, right? That's the second plot there, the second image there. Can anyone compare the first plot versus the second plot? What can you see now?
They are related. The second one is like the first one was squared up, or like having the absolute values, so there won't be any negative numbers, I guess. And still the
Okay.
relation of the number of parabolas is there.
Okay, that's great. What else can you see, guys?
The maximums are bigger. I mean, the height of the
Okay,
wave.
what does that mean? What does that mean? Because yeah, Natalia said the maximums are bigger. Fernando said it looks like it's the same, but it's a square or something. What does that mean in terms of, again, in terms of the meaning of this graph?
That the higher the level, the fewer the, I don't know, the probability to find that electron. Level of energy, I'm saying.
Okay, so can you repeat that? You said the higher the level of energy, the lower what?
The probability to find that electron.
Okay,
I'm
why
relating
would you
that
say that?
to the idea of the density function
Yeah,
that is
in which
applied
case,
in organic chemistry,
sorry,
where
I think,
the
go ahead, sorry.
okay, so in that idea, the electrons were more concentrated in the more stable levels of energy than in the higher levels. So that's why I'm saying that.
Okay. Where is the highest probability of finding an electron in the first level of energy?
Could be maybe right in the middle of the energy level because we
So
have
what
a
would be
peak.
that value?
Alpha divided into 2.
Yeah, alpha by 2, right? The value here is alpha by 2, and that's actually the highest possibility of finding an electron. It's alpha by 2. It's right in the middle. You can actually see something here, and this is a key concept in quantum mechanics. This is actually the deviation, or you can see here the deviation from the classical mechanics. This is classic. Give me 1 second. This here is classical mechanics. That's classical mechanics. They all thought, okay, I'm happy with that. Let's leave it there. But then the concepts of quantum mechanics appear. All these, weird, difficult concepts. And you say, okay, let's actually find the probability function of that. And you can see that for the first level of energy in quantum mechanics, actually, the deviation is higher compared to the other levels. What do I mean by the deviation? What you were talking about, Natalia and Fernando, you were saying it looks like the probability is a bit higher. It looks like it's the same function, but just a square. Well, that's actually the deviation, right? Compared to classical mechanics, in quantum mechanics, you see a deviation of the function, right? You see that, as you said, that higher maximum. Well, that deviation, it's the key concept is a key concept in quantum mechanics. And that deviation is telling me, in a more accurate way, what's the probability of finding an electron? In this case, I'm just talking about the potential well, which is actually a very nice case that describes a lot of things, and we'll see that later. And so if we keep escalating in levels of energy, what will happen? So let's say at n equals 7. What will happen at n equals 7? Well, the deviation will be even smaller. So I can see a big deviation in n equal 1, right? I can see a big deviation. N equal 2, okay, I still see a significant deviation. N equal 3, there is no much deviation. there is still a deviation. Obviously, now I don't have any negative waves, okay, any negative waves, because this is a square, obviously. I don't have any, and this is just a probability. Remember, this is a probability. And actually, if you remember, probabilities go only from 0 to 1, right? I don't have any other value of a probability, any possible value of a probability. It just goes from 0 to 1. So it can be negative, obviously, because this is a probability function. I already said that. So obviously, it's not going to be negative. But talking about the maximums, the deviation becomes smaller. So if I go to n equals 7, or n equals 10, or n equals 20, the deviation will be very, very, very small. So that means that actually quantum mechanics became really important for the first levels of energy. That's actually where it became so significant and say, okay, wait, actually, there is a probability, and the probability is much higher compared to the classical mechanics case. And there's another thing. If you see, let's say in the energy level when n equals 2, what's happening with the probability of finding an electron when n equals 2, guys? Who can answer that?
There are two different locations where I can find the higher density of electrons.
Yeah, where's the maximum? Where are those places? Maximum probability.
A by 4.
There will be 1/4 and 3/4, right? Or 1/4 and 3/4.
Yes.
Okay, it will be here. And what's happening with when alpha equals a half?
Probability 0.
Yes. And so and that's very important. So if I'm in level 2, the probability of finding an electron when alpha equals a half is 0. So I don't have any chance to find electrons there. Whereas I have the maximum probability when alpha equals 1/4 or 3/4 of alpha, right? Yeah. 1/4 of alpha or 3/4 of alpha. Is it clear, guys? Is this clear?
Yeah, sort of, mister. And we have a question. Why is the graphic becoming smaller if a square is supposed to be a constant?
Sorry?
In picture number B, well, letter B,
Okay.
the waves are becoming smaller, not like they are repeating more, and we already stated that's because of the period, but the probability is 4 times a square times sine square, whatever, but we can see that the graphs are becoming smaller each time n increases. Like, why is that happening?
Because
Aren't 4 and a supposed to be constants?
yeah, it's because of x. You have alpha and you have x there. And remember that you have, if you remember here, alpha is related to n.
Oh yeah,
right?
sure.
So n
We
is
know
changing,
that, but
and then you have x.
yeah. But I'm asking about the amplitude. What is outside of the sin square?
Oh, you mean, okay.
Yeah, like the size, it's becoming
Yeah, okay.
shorter every
You mean
time.
why you get in the first level, you get an amplitude of A, whereas I guess in your energy 2 level, you get an amplitude of A over 2 or half A? Is that the
No,
question?
I mean the height. The height of each wave. Like the first one, like it's higher than the other ones.
Okay. This versus this.
Yes.
And versus that.
That. Yeah, like it's becoming smaller. Why is it?
Well, that's just the value of probability. The height, it's this, right? And this is this. Remember this, let's say the y-axis. The y-axis is the value of probability. And the value of probability depends on all this. So alpha is changing because n is changing. So you will obviously get a difference in the maximum of the peak. What's being plotted here, guys, in the y-axis, it's the value of the probability. It's a probability value. It's that probability function of the wave function times its conjugate. And that probability depends on, yes, obviously depends on 4 and a squared, but also depends on this term. And this term depends on n, and n is changing. I have n equal 1, and then in the next one I have n equal 2, and here I have n equal 3. So that will affect my value, this term, and that will affect the value of the probability. Is that clear? Remember that alpha depends on n. Clear or no clear, guys?
Yeah, it's clear. David, I have a question.
Yep.
So as I go higher on the energy levels, let's say I have a energy level 20, let's say.
Yeah.
So I'm gonna have 20 waves, like let's say 20 peaks. So that would mean that I'm gonna have like 5% of probability to find an electron on those peaks. I mean,
Well, it's not linear. It's not linear. So I can say I will have 5% probability. But yes, you will have a high probability, let's say a high probability as high as the one that you will have in the first energy level. But the thing is, you have more probabilities in other parts of your of, let's say, actually of your electron, right? Because A at the end it's related to the atom, not the electron. Because let's say in that case of 20 waves, it will be something like that, right? And so on. So you will have more chances to find an electron, let's say, I don't know, let's say here in A over 20, I'm just inventing a number, right? In A over 20, whereas here maybe in A over 20 you have, I don't know, almost zero chance to find an electron. In that case, you will have, I'm not going to say a huge chance, but a bit of a higher chance of finding an electron in that position.
Yeah, but the wave that we're plotting with the equation, so it only shows like an average probability. Because in amplitude they will be the same. Or like, or does it change as I go higher in levels?
I don't quite get your question.
I mean, you said that yeah, I'm gonna have like 20 different positions, but some of them will not have the same probability as the other ones. So that means that
Okay.
as I go.
I'm sorry. Go ahead, sorry.
No, sorry, you were saying?
No, I mean, yeah, I was going to say, yeah, it will not have the same probability as, let's say, finding an electron in level 1. Yeah, for sure.
Oh yeah, but the different waves or the different positions
Oh yeah,
where I
yeah.
have my
They will all have the same probability. Yeah, I mean they all will
okay.
have this. Yeah, so it
Okay.
will all be the same height. Let's say. Okay. Yes.
Okay. Yeah, I got it. Thanks.
Oh yeah, yeah, for sure. No, it's not gonna change. It's not gonna be like, oh, that one is higher and then oh no, that it's not gonna be like this. Definitely not.
Thank you.
Okay. Okay. So what happened? So remember what we thought. Oh, sorry. What they thought before these concepts of quantum mechanics appeared. They all thought that the atom had the same model as, remember Niels Bohr model of atoms, kind of weird things. But then when they actually said, okay, wait, an electron, okay, I have, according to the energy levels, I have certain levels, okay, that the electrons can occupy, and also certain places or sites where I have a higher chance to find an electron. So they said, okay, it's not as easy as I have, let's say, I think they thought the electron was something like this, right? With the energy levels, this was the nucleus, and they say I have the same probability of finding an electron here than finding an electron here and here and here, and everything was the same. But they said, wait, I actually see that there are energy levels, and I actually see that I don't have the same probability all along the I don't know, the nucleus, because I think that's what they thought. That the electrons, basically, I had the same probability of finding an electron as long as I'm around the nucleus and at the same radius or the same distance of the nucleus, it will be the same probability. But then they said, they saw this and they said, wait, that's actually not real. Because I have certain places where I have a higher chance to find an electron, and there are places, according to the energy level, where I actually have zero possibility of finding an electron. Like that, or like here. In that, I mean, this will be quite complicated to explain if I were to fully explain this. But then that's why they say, okay, so electrons aren't actually moving in a circle, or yeah, let's say like all around, like the planets. They're actually, because I think that's what they thought, right? Like planets around the sorry, like planets around the sun, right? That's what they thought. They're moving always like that, and I have another planet that's the next energy level, and it's always around the sun. Then they realize, no, that's actually not the case, and that's where the Rutherford model appeared. Do you all remember the Rutherford model? Well, it's this one, right? Remember Jimmy Neutron? Did you guys see that cartoon? Well, this is the Rutherford model.
Yes, sir.
Yes, that's the Rutherford model. And that's how they say, okay, wait, actually, there are certain energy levels, yes. And electrons will be moving on that energy levels in certain spots. And that's why this complex shape of an atom appeared. This is called the Rutherford model. If I'm sure you guys learned that maybe in high school. And it's all related to this. So this concept that seems easy, but at the same time a bit abstract, actually gave light to what we all know an atom is, what in present times. And that model is actually related, again, to how the electron moves. Because they say, okay, wait, So the electron is coming here, right? Let's say it starts here, right? So an electron comes this way, comes that way, but remember that I can approach, so I don't have, I have probabilities of an electron becoming zero in certain spots, right? So it's not that, oh yeah, it can come here and it can actually close the loop or whatever. Because remember that I have zero probability of finding an electron, let's say for the first energy level, right? I have zero probability of finding an electron at when I have a value of A, like exactly A, or 2A or 3A. So the electron is not gonna move, let's say, to the nucleus, okay? Or when I have a value of 0, right? I have zero probability. So this, I mean, it's obviously more complicated, and I don't think it's worth the time to explain this, but the concept is, or I guess the key part is how the electron, or sorry, depending on the probability of finding an electron, they said, okay, the electron moves around the nucleus this way, and that gave light to this model that we all know, the Rutherford model, the concept or the modern concept of how an atom is, and especially how electrons move around an atom. Okay. Is this clear, guys?
Yes, Mr.
Now, it's time to talk about what matters for us the most, the solid state. Because we talk about solids in this, in general, most materials you learn, you barely learn about liquids, you barely learn about colloids, you barely learn around gases, right? You do learn, but not much. And the materials you actually focus on are all solids, right? Metals, ceramics, polymers, they're all solids. Right? Polymers, you could claim that, but at least metals and ceramics, they're all solids, right? In this new sub-module, it's titled Electron in a Periodic Field of a Crystal. Why, when you see this periodic field of a crystal, and I already mentioned that this is actually the case of the solid state, why do you think the solid state is a periodic field of a crystal? Or basically, you try to represent the solid state with electrons in a periodic field. Do you guys see any connection between the solid state and trying to represent that model, or those models of solid materials, with electrons?
May you ask one more time, please?
Okay. We've seen different cases so far. We saw the free electron case. We saw the electron in a potential well. And those cases are all well known. And at some point, it will help us to represent how electrons move in certain solid materials, but in specific parts. But there is a model that represents very accurately how electrons behave in solid materials. And that model, it's called electron in a periodic field of a crystal, this model. So why do you guys think a periodic field, or this model of electron in a periodic field, is chosen to represent the solid state? So it's chosen to represent a solid material, or how electrons behave in a solid material.
maybe because in a unit cell, in a crystal unit, you have like a certain behavior of electrons. So since a solid, it's full of crystals, well, crystal solids are full of crystals, so we're gonna repeat that unit or that behavior through all the crystal section.
Perfect, Natalia. That's the question. That's the answer. What happens with solid materials? And again, especially talking about metals and ceramics, right? And semiconductors. They're all crystals. What's a crystal? Or sorry, they're crystal. They are crystalline materials, right? We're not talking about glasses here, so let's assume for the rest of materials, they're all crystalline materials. What means a crystalline material? I have periodic units that are repeating constantly, right? The unit cells. So that's why you use this model of a periodic field, because it's the same that is happening in a solid material, because you have a unit cell that is repeating each time and it's forming my my crystal, and in you know, the union of the of different crystals is forming the solid material. It's forming the material itself. So that's why you choose this concept or this model of electron in a periodic field. Okay, and that's what you see here. It's and that was the first task, right? Because they already came up with this free electron case. They already came up with the free the electron in a potential well case. But they said, okay, now let's find a distribution or a potential distribution that can represent a solid, because that's, again, that's the key part of materials, right? Ceramics, metals, they're all solids. So how can I represent that? And again, as Natalia said, we all know, and we've already learned by now, you're all experts on that, I think, that atoms in a crystal, in a solid, are arranged periodically, right? And that's the unit cell that Natalia was talking about. Therefore, what model I'm gonna use? Well, obviously it has to be periodic, and it's actually a periodic arrangement of potential wells, and obviously potential barriers, right? Something like this. Sort of the same case as before, just now that it's periodic, so I have to repeat and repeat these barriers over and over and over again. So it will be, before I only had this, right? The potential well. Now the idea is to repeat that over and over again, as such as, you know, atoms are arranged periodically, so unit cells repeat over and over again. Same here. I'm gonna repeat these potential wells over and over again to represent how electrons are behaving in a solid. Is this clear, guys? This is obviously a simplified model. This is actually called the chronic penny model. Okay, obviously the 1D model, no, the simplified model. Okay, so from that graph, guys, what's the length of the potential well? What's the length of the potential wells?
A.
Perfect, Miguel. It's A. It goes the potential wells, a potential well. Let's just focus. Let me this one, right? This length, it's goes from 0 to 8, so it is A. Yes. What's the height of the potential barriers? or of the potential walls. What's the height? I don't think it's infinite. Let's see the graph.
V0. I don't
V
know
naught.
if that's the
Yeah. V naught.
V naught.
V naught.
V naught.
Yeah. It's V naught. Yeah, it's V naught. It's not infinite, right? It's not an infinitely high barrier. It says that it has a limit, and that limit in this case is called V naught. Yes.
But what? Sorry to interrupt. But what does V naught means? I mean, is it the
It's just a value.
voltage?
It's just a value. It's yes. It's a potential energy. V naught, it's potential energy. That's why it's called potential wells. It's potential energy that, if you remember from the first class, from last class, I don't remember if you were there, Natalia, but remember that basically the big Schrodinger equation, the basic Schrodinger equation, has this concept of E minus B. So that's the total energy of the electron. And I have always to subtract the obstacles the electrons have to overcome. And those obstacles are basically, in this case, are these wells, these potential wells. And well, that energy is the potential the potential energy that is represented here, that in this case it's called V naught. If you go back to the Schrodinger equation, remember we have this term, guys. And that's important because that basically is representing the total sort of the energy of the system, right? Or the energy that the electron needs. And that's E, the total energy of the system, and B, it's the potential energy. That is sort of the obstacle for electron movement. Is that clear, Nathan?
Yeah, it's clear. I remember from the last class. Yeah, thanks.
What's the width of the potential barrier?
It's B.
It's B, perfect. It's B, right? You see, that's the width of the potential barrier. Now, we're gonna assume something, and this is actually the assumption they made when they were developing all these models. We're gonna assume that B naught is larger than the total energy of the system. Or sorry, the energy of the electron, than E. We're gonna assume that B naught is larger than E, than the energy of the electron. This is actually quite a good model, represents quite nicely how electrons behave in solids. Obviously, there are, let's say, certain things that should be considered in this model, but obviously for the simplified case, they're not being considered, right? For example, this model doesn't take into consideration that inner electrons are more strongly bound to the core. So electrons in the first levels obviously are more strongly bound, so that means they have higher attraction to the core compared to electrons that are in outer levels, right? And I think we all know that, right? I think that makes sense. That's something, it's not represented here because obviously this chronic penny model, it's a simplified model, but it works quite well, actually. Okay? So with these considerations, guys, can anyone write or tell me, it's not right, how, well, first of all, how many Schrodinger equations I'm gonna write? Remember that all these models are represented by the Schrodinger equation. So how many different situations I have here?
You have pretty much the same, it's just repeating over and over again.
Yeah, okay, so how many equations will you write? How many
Only
case
one.
scenarios do you have?
Where is one? Because in general there are infinite, as there may be infinite periodic
Yeah, well, this is actually infinite.
periodic stuff.
This keeps going on and on and on forever. But to represent this, how many do you need?
Only one.
Only one. Okay.
There are two regions.
Yes, I need
First
two.
one
Okay.
is related to the free electron, and the other one is to with the restrictions. So I think that the more important one will be the second region.
Yes,
I mean,
but I need both, right? Definitely, right,
yes.
Miguel. That's correct. I need two equations. I need two Schrodinger equations here. I need region one, as Miguel said. Region one is just the free electron case, because basically in this region it's electron moving freely, right? So it's this case. Remember, it's the same case as the free electron, right? Where alpha, we all know what alpha is, right? Or how alpha is related to E. I think we all know that. This is already, it should be already in our minds. In the second case, well, the second case, it's basically the full Schrodinger equation, just that I've replaced the value of B, because now it's not called B, now the value is actually called B naught, so B naught, okay, B naught. I think that's clear, right? And I'm just gonna use gamma. I'm gonna use gamma to call this term, okay? That constant is, I'm just gonna call it gamma for now. And remember, I say this because remember that B naught is larger than E, right? I said that is actually the case. That's the assumption they made, and that's actually the case. B naught is greater than E, than the energy of the electron. Okay, so this is just okay, an annotation, okay, and just to make it all positive, but let's just keep there. I mean, I just leave the equations there, but what I really want you to understand is how do I describe this, okay? And that's these two equations. The first one with Hindewell, well, that's just a free electron case, and in the well, so I mean, sorry, in the barrier, what I have is, well, I have a potential energy called B naught, and then everything else is the same. Okay, so I have these two equations. Now, okay, let's solve these two equations. If I want to solve this is definitely quite complicated. If we have time, we might do it in a tutorial. As I said, I don't want you to become mathematicians here. But that will take a lot of time to solve them. But I'm just gonna give you something. I'm gonna give you the solution. And it's actually with this block function. I'm not sure if you ever saw this function. But block showed that the solution of this type of equation, okay, so this system of equations can be given by this form. And this is actually called the block function. Okay? Where U, it's a periodic function, because remember that this is all a periodic system. U is a periodic function that possesses or that has the periodicity of the lattice in the x direction. So what I'm saying is, okay, if the lattice, remember, what's the lattice constant? It's A, right? And the periodicity is actually A. So this is A, this is A, And yeah, I can have another one here that would be A. I can have another one here that would be A. So u of x, this function here, is a periodic function, and its periodicity is equal to the lattice constant. Okay, so in this case, it will be A. So, what's different now with u of x compared to the other cases? Right, where we had only one well, now I have a periodic arrangement of wells. What's the difference? Well, now u is actually not a constant, because remember what did I have before? I had a squared, right? So it was a constant. Well, now this is not a constant. Sorry, it will be this one, right? 2a. Forget about that. 2a, but that was a constant. Well, now it's not a constant. Now it is a function, right? And it's changing periodically as x is increasing. Okay, so I guess that's the big change compared to the previous case we had before, the electron in a potential well. Now I don't have a constant, I have a periodic function with the periodicity of the lattice constant, and that is changing periodically with increasing x, or with increasing modulated amplitude. Okay, and obviously this function is going to be different for various directions in the crystal lattice, right? And this part, well, this part it's the same, right? Times e to the I k x. So that's something we already had before. This is the key term that's changing now. This is called the Bloch function. So Bloch developed the solution for that equation, and he developed the solution, obviously. And you know, again, this is pure mathematics. We can solve all this, and it becomes quite a long exercise, and we finally get this solution. Okay, we can solve with the Bloch function these two equations. We can get this. Sorry, we can get that equation where p is a constant, because P only depends on the mass, the lattice constant, the potential energy. B, remember, that is the width of the potential barrier, and the reduced Planck's constant. So P is a constant, okay? And that's the solution. Again, I don't want you to become mathematicians. I don't want you to learn and solve this. That will take ages.
I have a question. Does P represent something special? I don't know.
Nah, not really. I mean, you can use it just as a value, but it's basically a constant. But it's not really. I mean, it doesn't really have any physical meaning, if that's your question.
Yes, that's my question.
It doesn't really have any physical meaning. No. It's just a constant. You can call it any name. It's just a constant. So this relation actually provides the allowed solutions to this equation, right? To these equations. So that's the relation that allows me to get the allowed values of energy, you know, in the Schrodinger equation. And these boundary conditions that I had, it led to a solution that has trigonometric functions involved, right? Such as we got in the previous case. So we also had a trigonometric function as part of the relation. It was actually a sine function. So now we get a sine and we get also cosine of these values, right? Of the cosine functions. Now, question here, guys. When you see this relation, remember that this will be the key, or I can use this to solve the Schrodinger equation, right? And remember that the Schrodinger equation gives me the energy values that an electron can get. So when you see this relation, do you think that all values of energy will be allowed? Or will we again get an energy quantization? So that means only certain values of energy. I'm going to simplify the question. Is any value of alpha allowed to satisfy that condition? Come on, guys. Can alpha be any value?
There's a mathematical restriction where it can be 0, but other than that, we had this previous formula. I don't know if it's valid yet, which said that alpha was the square root of 2 times m times energy over the modified Planck's constant square.
Yeah. Yeah. It was valid for the free electron case, remember. And for the electron in a potential well, just for the first part of it, right? Remember that then we had another value of alpha. Should be somewhere. Yeah, so we get this for alpha, right? And we get this for alpha, right? To remember that alpha take different values according to the case, right? Okay, just looking at this equation, guys. Do you think alpha can take any value? Yeah, obviously it can be 0, as Fernando said, because if this is 0, that will be divided by 0, and that will be infinite, and that obviously makes no sense.
I think that there won't be any restriction.
Okay, there will be restrictions for sure, because I have to satisfy that, well, this term, remember that k is not arbitrary, right? K is also a value that depends on lambda, right? K is the wave vector. And I have to satisfy this. I have to satisfy cosine of the wave vector times the lattice constant. That must be equal to this term. That, yeah, it's a complicated term, right? And I mean, if we try to get easily a restriction as we did last time for the potential well case, where I guess it became so obvious here, right? It became so obvious when we got this. It became so obvious. Oh, okay. So alpha must be an integer to satisfy this, right? That was what we get. What we got, sorry. Sorry, A must be an integer and alpha. So it was quite obvious. Here it doesn't. I guess it's not as easy to realize as in that case. But it is, I mean, there will be certain restrictions because I have a sine of alpha here. I have a cos of alpha here. This is obviously divided by alpha. And that must be equal to the cosine of the wave vector times the lattice constant. So I could solve for A here, you know, and then try to see any restriction. But I guess we can all see that it won't be easy, and it won't be that the case that O alpha can take any value, because not any value will satisfy this condition for sure. It won't be as easy as that, right? Alpha will not be able to take any value. Therefore, again, and we can plot that function, right? We can plot it. It will be something like this. If you plot it, that's the function. You can plot alpha times A versus P sine alpha over basically versus this, right? Versus that. You can plot it, and you can see that the function takes a certain shape, right? And this already gives me, an indication that only certain values of energy can be get. Why? Because remember, this term, guys, is only defined from -1 to +1, isn't it? The cosine of a function, in this case the cosine of Ka, it's only defined from -1 to +1. Unless I have imaginary values of K, it's only defined from +1 to -1. That's why you see there are lines here sort of restricting that. The allowed values of this function, okay, therefore will be restricted only to +1 and -1. Therefore, this will become a gap. This will become a gap. And this will become a gap. And that will become a gap. And so on. Therefore, an electron that moves in this periodically varying potential field, in this potential infinite one, can only occupy certain allowed energy zones. Energies that will be outside these zones or these bands are obviously prohibited. And something that you can realize is that as I increase alpha A, as this becomes bigger, the bands, the forbidden bands, become narrower. Because here you can see, oh, that's a huge band that is that is prohibited. Okay, that's a smaller band. That becomes even smaller here. That becomes almost, it's quite difficult to see now. And I can keep plotting this. You know, it goes periodically. But these bands now, let me charge my computer. Where is it? But this now becomes narrower and narrower. So as I increase alpha, sorry, as I increase alpha A, the size of the forbidden bands becomes narrower and narrower, and you can definitely see that. Here's bigger, here it becomes narrower, even narrower. So as I increase it, the size of those forbidden bands becomes narrower and narrower and narrower. What does that mean, guys? Well, I guess let's see it in a clearer picture. Free energy case, electron in a potential well, electrons in solids, in periodic field of crystals. So now these gaps, as I said, first of all, I don't have any lines anymore, right? It's not just a line. Now it's actually a band. You can see now it is a band of energy. And also, as I increase the energy level, you can see that these bands become wider. And that is related because the prohibited, these spaces here become narrower. And this is the cases of a solid. Energy bands. These are actually energy bands. In the periodic field case that we saw before, it's more of like a periodic line of energy. Question, guys?
Yes. So in the right image, we are seeing the sum of all the values of, or a certain amount of values of A applied to the previous equation, the previous graph. So we are not seeing, for example,
No, this is actually the
alpha.
energy. Wait. First of all, this is actually energy, right? In this case, we are not plotting energy. There is a relation, yes, for sure, because remember, this equation, that is the one that is plotted there, well, this relationship actually, that is the one plotted there. This equation allows me to get the solutions of energy for this equation, for these two, for the Schrodinger equation, right? So with this relation, the relation I have here, and part of this relation is this plot that I have here, right? I can get the values of energy. So there's not a direct relation, but it's definitely correlated because I know that here, sorry, there are certain gaps, right? That I know when I use this relation that's basically plotted here, these gaps that I'm not allowed to use here, right? these spaces, will become evident once I get the energy values, and I know, oh, here I don't have energies or values of energy allowed, and that's why I get these gaps here. And that's why I have these allowed values or bands of energy allowed at certain levels. So it's not a direct relation, but yes, it is related.
Okay.
I have a question. These energy bands shows the behavior of one single unit or the whole structure.
You mean of the crystal? No, this is already the periodic in the periodic field of the crystal. So that means in the whole crystal. Sorry, in the whole, yeah, I mean in the whole arrangement of the material. So not only in one unit cell, but in all unit cells.
Okay, thanks.
Another question, guys? Okay.
May you repeat what the second picture means?
Second picture.
B, letter B.
That's a free electron case. So that's the energy continuum. So remember, in the free electron case, this one, we have an energy continuum. We had no restriction of values of energy, remember? So what we plot here in the y direction, it's energy. So I have no restrictions. I have all values of energy allowed. No restrictions in the free electron case. So the letter B is basically the free electron case. So that's why I call it summary, this, because so far what we've seen is the free electron case, picture B, the electron in a potential well, picture A, and the electron in a periodic field of a crystal, or the I guess the better meaning and interpretation of that case, electrons in a solid, picture C. Is it clear, guys?
Yes, mister, thank you.
Okay. Time for coffee break. Please, Joshua.
Yes, I'm gonna share this with you for a while. And you can see my presentation.
Yes.
But I can see my computer. Now,
What's the problem, Joshua? I can see your screen.
but it's not completely the screen, full
Yeah,
screen.
that doesn't matter. I mean, if you I can see it clearly, so that there's no problem. You could just explain like this way. That's fine. No worries.
Okay, but let me see if PowerPoint doesn't respond the clip that I've been.
Yeah, okay. No worries.
I can't go to the next slide because my
Maybe
computer
close the
is
presentation and open it again. Okay, so
try
that
pressing
occurs.
F. I'm sorry, teacher.
Sorry, Miguel, you
But
were
I
saying.
think that, yes, maybe Joshua can try pressing in the keyboard F5 to present.
Yeah, but my computer doesn't respond. It's my computer.
Okay.
Okay. Okay, in the meantime, I have a question from Jose here. It says, picture C is the representation of the block function. And this function is for both cases. I mean, picture C becomes, yes, I would say it becomes a representation of the block function, yes. And this function is for both cases, the free movement of electron in the other one case. Yeah, I mean, yes, this function, the block function, basically gives the solution of these two cases. Remember, because what we did is define the Schrödinger equation for the two regions, right? For the region where I have a free electron movement, and for the region where I have the barrier or the wall, right? So yes, so the block function is basically sort of it's sort of, let's say, giving a way to solve this case. So yes, it's basically a solution to both cases. And yes, we could say that picture C, I mean, I wouldn't say it's really a representation of the block function, because well, I would say it's actually a representation of the block function becomes the picture of the waves. Remember the function itself that we saw with all the parabolas? That would become a more accurate. If you want to claim, okay, what the representation of the block function is, it will be that picture. Because picture C is actually the case once you solve the Schrödinger equation, and you get, oh, okay, so these are the values that are allowed. And then you know, you get that once you solve the Schrödinger equation. So I wouldn't say C is actually a representation of the block function, but it is related at the end, because remember that picture C is developed by the block function, by that function that we saw with the parabolas and constant parabolas, and as alpha A increases, that those restrictions become narrower, remember? So it is related to that, and that is a representation of the block function. So you could say, yes, it is related. But yes, the block function is basically associated to the solution of both cases, because at the end, those two cases is what, or those two cases are representing the whole system, right? That is arrangement of atoms in a solid and the movement of electrons in that solid.
Mr.
Sure.
Natalia is gonna share my presentation because my
Okay.
computer doesn't report.
Okay, go ahead.
Nati, please.
Okay, nice, Jose. Okay, let's go.
Okay, and I choose to talk about the photovoltaic glass, and the next slide, it's gonna to share with you the problematic. The next slide. Okay, when we speak of solar energy, we directly classify it as a renewable energy, and one of its disadvantages is the space that is needed to deploy the solar panels, which is often done in rural areas because in the city it's more difficult to solve. There are some houses and small buildings that can install solar panels or solar tiles on their roof. However, for large buildings and skyscrapers, this measure is insufficient. In the next slide, for this reason, the alternative of photovoltaic glasses arise. Next, the composition. Photovoltaic glass can absorb the sun's rays and transform them into energy. These glasses have a photosensitive coating, The interesting thing is that it could be used in other objects such as vehicles with a solar roof or cell phones. In next slide, how does it work? It consists of layers of amorphous of crystalline silicon. When it comes to amorphous silicon, it consists of three layers. The first has a transparent semiconductor, the second is a deposit of amorphous silicon, and the third contains an aluminum deposition. In this way, the photovoltaic windows traps the photon and of the solar radiation to generate electricity. Now, and then, yes, this new technology selectively exploits a part of the solar spectrum that is invisible to the naked eyes, while allowing normal visible light to pass through, as we can see in the image. It is based on a transparent luminescent solar concentrator, TLSC, that thanks to this, the organic salt that TLSC is made of absorb UV and infrared and emit infrared process that occurred outside the visible spectrum, so it appears transparent. They can filter ultraviolet radiation by the 99% and infrared by 95%. In this way, they thermally insulate a building and protect it from radiation. In the next slide, we have the advantage. Next slide. Next, please. Okay. Um, it doesn't need a space because they adapt to different spaces, and it available of different shapes. Photovoltaic windows have different types of size, shapes, measurements, colors, transparencies, and more. This favors customization and adaptability. Insulating and protective qualities. By absorbing ultraviolet and infrared rays, glass acquires insulating and protective qualities for space, helps keep rooms cool or convert sunlight into heat, reduce the need for external sources, and it is also easy to install. They can be installed in a wide variety of places, including windows, arcade cards, phones, tablets, and more. Disadvantage: we have the low efficiency compared to the traditional solar cells, although its performance is expected to reach up to 15%. Thanks.
Okay, thanks, Joshua. Great topic. Actually, quite interesting. I have three questions. The first one: did you say? Well, there was one contradiction for sure, because at some point you said amorphous crystalline silicon, which doesn't make sense, or it's either crystalline or amorphous. But at the end you said that actually there's one layer of amorphous silicon, right?
Yes, because these glasses are made of they can made of amorphous, but they are also made of crystalline. But they are combining these amorphous and crystalline. Of these, for this reason, they are they also they are not always transparent. They could have a little color, and depends of the crystallinity, they loses her transparency. And yeah,
Okay.
I respond.
So it is not completely crystalline, or is it that they're using two layers, let's say, one crystalline and one amorphous? That's not clear to me. Or is it a semi-crystalline silicon that they're using? Because if we're talking about, for example, solar panels, solar cells, they use crystalline silicon, 99.9% crystalline silicon.
But these principles are made of amorphous, but they
Okay.
they can take a little fraction of crystalline, but normally they are amorphous. But these give them the transparency. So
Okay.
the principal characteristic is they are amorphous.
Something else didn't wasn't clear to me. Is it are they being used for to generate electric energy?
Yes, they the the spectrum of the light have
Yeah.
different wavelengths.
Mm-hmm.
So these crystals, these glasses absorb the ultraviolet and infrared, and they let pass the visible light.
Yeah.
So the the silicon, okay, the silicon, no, this energy from the UV lights and the infrared light give the enough energy for the electrons of the silicon to move, and for this they can generate energy only
Okay.
with the UV and infrared light rays.
Okay.
But they are obviously with they are no not with the complete range of the wavelength. They not generate so much energy like the normal cells.
Yeah. Okay. Yeah. I mean, obviously they're not gonna get the same efficiency if you're saying they're using amorphous silicon. It will be quite difficult for electrons to move in amorphous silicon. That's why I'm surprised. It'll be interesting to see actually how they develop that idea, because yeah, if it's amorphous, the electrons will have a lot of barriers to move in order to move, and obviously that's what that's why they are losing efficiency, right?
Mhm.
Um, but I guess because you were saying that they're also trying to take the advantage of sort of not needing air conditioning, because from what I understood, this material is also sort of absorbing the heat and just retaining it, right? Not letting it come through the glass and obviously penetrating into the room. Was that right?
Yes, because they absorb a part of the rays. They contain a little of it, and the room could not get it so much as normal.
Okay.
But not it
Yeah.
doesn't have a cooling effect. It just to doesn't permit that
Yeah. Yeah.
the light
Yeah. I
penetrates.
get
So
that. Yeah. I get that. Okay. Yeah. I mean, for that, yeah, it makes sense to use amorphous silicon. Because remember, at the end, what you all took already ceramics. Remember that the end glasses are silicon oxide, right? Um, and that is amorphous silicon. So I don't know. It's actually quite interesting. I mean, I'm actually quite keen, and I'm gonna research on that just because it's quite interesting to me that they're using amorphous silicon for that. Um, Did you see it where they are actually using this? Like already using? I already saw some pictures there that seems
yes,
that already.
they are using in buildings because if normally panels can be put in on the roof
Yeah,
of houses, but in a building the area of the panels will be smaller. So for this reason, they develop these materials to replace the windows. But it is also being developed because the efficient.
yeah. No, I get that. My question was in which countries or which cities are already adopting this, or what city has been implemented this into? Did you see that?
No, I didn't see, but I imagine that USA have them.
Okay. Because I imagine I mean, it's not efficient, so I think they're spending a lot of money on this. If well, I guess it's also not expensive if we're talking about amorphous silicon, but I mean, it sounds a bit controversial in terms of going to the market and using this. It seems like it might bring more expenses at the end, at least until you get a higher efficiency. But okay, interesting. I'm gonna research on that. Especially the materials they use for that. But yeah, quite interesting topic, Joshua. Thank you. Does anyone have any other questions for Joshua? Okay, I'm gonna continue with the class then. Thanks, Joshua.
Thank you.
Okay, let's see what we get. Okay, so let's just try to relate E and K, the energy and the wave vector. In the case of free electrons, you can get back to the equations, right? You can go back once I upload this slide or just your notes, and you can see that there is a simple relation, right, between K and E. It's actually that K is a constant times the square root of energy, right? And that's the simplest case for energy electrons. So now what we learned so far, okay, allows us now, or we're now in the position to actually make important statements that will contribute considerably to understand properties of crystals. And that's what we're starting to do now. Okay, we saw a lot of theory and a lot of sort of abstract concepts, but these concepts actually now allow me to understand a bit more what the properties of crystals are and how are are they produced. So we plot here just energy versus the wave vector, or the momentum versus the wave vector. Remember, momentum I can relate it to energy. We'll get something like this, right? I think we all agree on that. It's just a parabola, right? And all values of energy are allowed, no restrictions. That's the case of free electron. Now, let's go to this case. Imagine this case. What happens in this case if P equals 0? Oops, sorry. What happens if, let's say, for some reason we get P equals 0, and for P equals 0 actually will mean, actually that's the question. If I get P equals 0, what does that mean, guys? That P equals 0. What will be that case?
Will be
We
the
have
case
to
for free.
quantize.
Sorry? Miguel and Natalia talk at the same time. Okay, let's go, Miguel. What will, if P equals 0, what does that mean?
That we are not having a a region. Instead, we have a potential in like a line, and it's related to the quantization of the energy.
Okay. Natalia, what do you think?
Maybe that means that we're not having tensional energy, so maybe free will be the case for free flying electrons.
Yes, that's actually the right answer. I mean, yes, remember, Miguel, that P is equal to B. I mean, P depends on. Oh, sorry, I don't have a pen now. Yes, okay. So P depends on B naught. The mass can be zero. The lattice constant is impossible to be zero. The reduced Planck constant is not going to be zero. So what has to be zero for P to be zero? B naught and B, right? So that means I have no barrier. I have no barrier. I have no potential barrier. Then it will be zero and this whole term will be zero, right? So that means the free electron. So if I have a free electron, actually, this equation will become that, right? That is what I have here. The cos of alpha A will become the cos of K times A. Do we all get that, guys?
Yes, mister.
Okay. If we want to expand this equation, right? Because we all know that the cosine function is periodic in what? In 2 pi, right? Remember that the cosine function is periodic in 2 pi. We all know that. So I can expand that equation, right? And because we're talking about periodicity at the end, then it will be n2 pi, right? Where n will be plus minus 1, plus minus 2, and so on. Therefore, alpha A actually becomes Ka plus n2 pi, right? So I can solve for that. And I can say, because remember that alpha A, if you solve here, right? Let's just remember. Give me 1 second, okay? In order for you to get this, what is this equal to, guys? That's equal to right? Remember that alpha is also equal to this for the free electron, guys, isn't it?
Yes.
So here what's happening, you're just only solving for alpha, right? Alpha is equal to, you can solve for alpha, it will be n2 pi over a plus kx. So that's alpha. This is alpha from this equation, right? Oh, actually, that would be probably best. Alpha is equal to that. And we know that for the free electron case, alpha is also equal to this, right? And remember that was already taught in last class. Do we all follow that, guys? Is that clear so far?
Yeah, it's clear.
Okay. So therefore, in this general case, what's happening because of that, the parabola is being repeated periodically in intervals of n2 pi a, right? Therefore, the periodic, or this energy is basically a periodic function of the wave vector with a periodicity of 2 pi a. So if we were to plot this actually with this periodicity consideration, it would be something like this, right? Where the periodicity is 2 pi a. See, that, and that, and it keeps going and going, right? Here we got the periodicity, okay? And we can plot that, and we know that in this general case, right, the parabola will be just repeated periodically in intervals of n to pi a. And n, remember, can be an integer, either positive or negative, and can also be 0. And therefore, this energy function is just a periodic function of k with a periodicity of 2 pi a. Okay. And that's the plot of energy versus the wave back. Sorry?
Can and
No, el que está dentro del baño. Y pones esos, eso de los hornos, ¿cómo se llaman? Las bujías. ¿Hay video de eso? No, ahorita no.
Yeah, you can type your question and I can answer it towards the end of the class. We're about to finish the class. Okay, so now let's go to the periodic potential, right? We noted that if an electron propagates in a periodic potential, there are always discontinuities, right? And remember that there are discontinuities, right? It's not like this case. Remember, this is just free electron case. No discontinuities. It just keeps going and going, no discontinuities, right? But for the potential well, for example, and even better, right, for the periodic potential, that is just sort of a repetition of the potential well, there are discontinuities of the energy, right? And the discontinuities are when, remember, the cosine of the wave vector times the lattice is either minus +1 or -1. It's when they reach the maximum, right? Remember, it's like I cut this, cut off this, cut off that, cut off that, and those are discontinuities. Right? And that's why, then you plug that back into the Schrodinger equation and you get these discontinuities of energy. There are discontinuities. Now, for cos of the wave vector times the lattice constant to be equal to 1, that means that kxa, so the wave vector times the lattice constant, must be equal to n times pi. Remember, right, that the cos of pi is equal to 1, right? Cos of 2 pi is equal to 1, and so on, right? We all know that. So the maximum or the minimum will be satisfied as long as this term kxi is equal to n pi, n being any positive or negative integer. And therefore, from here, I get that the wave vector is equal to n times pi over a. This value of kx now is quite important because this consideration leads me to what? That the electrons in a crystal behave for most kx values, for most values of the wave vector, they behave like free electrons, except when that wave vector value approaches the value of n pi over a. This value. So that means when an electron is away from this in a crystal, when an electron is away from this kx value, away from the wave vector being equal to m pi a, electrons in that crystal are behaving like a free electron. But when they're approaching m pi a, so they're approaching, let's say, 1 over pi a like this, or 2 pi time, over a, or 3 pi over a, the function decreases, the value of the energy decreases. But away from those values, so here, 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 they're behaving like free electrons. Like that parabola we saw, remember? This one. With no discontinuities. Except when I have the kx, or the wave vector, approaching m pi over a. Is that clear, guys? If you see, actually, what, and this is great. If you see the dotted line here, I'm sort of trying. You see the dotted line here, right? The dotted line, this one, I'm gonna try to plot it actually like this. What is this? It's this. E equal constant kx squared. So, and this is what I was saying. When kx is away from the m pi a value, okay, remember, this, when this approaches that value, let's use another coloring. Just let's focus on this part. Let's say this one. When it approaches this value, 3 pi a, right? What happens? Oh, there is a discontinuity. But then when it's away, it's basically following the same path of the free electron. Look, that's the same path of the free electron. Oh, it approaches that value. Oh, okay, sorry, discontinuity. And then, oh, okay, now you're away from that value again. Oh, okay, then you follow the same path of the free electron. Sorry, the same behavior of the free electron. Oh, again, discontinuity. And then again, the same behavior of the free electron, and again, discontinuity. And this just keeps going and going and going, and can go forever, right? When the wave vector is approaching the m pi a value, then I have a discontinuity, so it's not behaving as a free electron. But when it's away from that, it is behaving as a free electron. Is that clear, guys?
Yes, mister, it's clear.
Okay. So Natalia said, can n be 0? N for what? N in the you mean, I guess, in the last case where the wave vector is equal to m pi a, right? Do you mean there, Natalia?
Yeah, we had a kx plus n by, yeah, that one. Yeah, this one.
This one.
Yeah, can n be 0? 'Cause, yeah, I saw a 0 here.
Yeah.
In this case.
I see. What did Jose say? I don't think so. I miss the energy bands. Well, n doesn't mean the energy band. I mean, you can say that when n equals 1, that will be the first energy level, but that's not really, I mean, sort of a more, it goes farther than that, right? It's not really that. N can definitely be 0 as long as it satisfies the condition, right? And in that case, let's say you will say that the first level of energy is actually kx equal to that, right? And that will be your first level of energy. So n is not really, n is just a number that you put that it can certainly sort of satisfy the periodicity of the function, but that's it. Yes, it's usually related to the level of energy, yes. And by the way, level of energy is not the same as energy band, okay? So watch your words, guys, because I see Jose saying n means the energy bands. I guess what you meant to say is the energy level. That's not the same. Any questions, guys? Any other questions? Okay, I have to run to my other class, so I'll see you all on Wednesday, guys. Take care. Thank you for joining. You can write me any questions if you have. I'll answer after my other class. Thanks, guys. Have a good day.